Okay, so what we're going to do here is we're going to review chapter 4 of the Understanding Photovoltaics. So I'll go ahead and jump into that. Let me share the screen. Here we go. So starting the quiz, hopefully there, can you see the screen that I'm sharing? Is that good? Okay, great. All right, so this is all just basic electricity. So if you have a background in electrical, a lot of this is going to be review. If not, just shout out any questions you may have as we move forward. But the amount of flow or current is measured in amps. Of course, the water analogy is one I always like to use, most instructors do, saying that basically if you're thinking about power as the amount of water that's flowing through a pipe, then amps is the size of the pipe and volts is the pressure under which it's flowing. And both are required for things to move, but they're different in aspect. All right, when there's an imbalance between positive and negative, at the terminals of the battery or whatever, there's a difference in potential. This difference is measured in volts. And what we're talking about there, of course, is if you think about what is a volt, you know, why do we say it's 12 volts versus 8 volts versus 600 volts? It's usually just a difference in potential from a reference point. And we just refer to zero or Earth as zero, which is our reference point. And that's a purely arbitrary thing. It's just that we say the Earth is at 0 volts. And so that's what we're going to reference as zero. So if you get a positive or negative, that's just the difference between 0 and wherever you happen to be, a difference in potential. Which of the following is not a safety recommendation when working with wires? Well, always check and test exposed wires, making sure no current's present. That's true. Don't assume, even if you've turned something off. Wear goggles, that's a good idea if you get an arc flash. Use protective gloves, wear insulated shoes, that's a good idea. Wear a respirator, no, not necessarily required. Respirators are used primarily when you're working in an enclosed area, like an attic, or if you're working with some sort of, you know, something giving off fumes. So we wouldn't need that for working with electricity per se. Watts equals, well, this is going after the power equation. So watts equals amps times volts. And this is one of the equations that you're going to need to know for the test. It's just watts power equals amps, which is current, times the pressure or the differential in potential. Watts equals amps times volts. And of course, we will refer to that as W equals I times V. V is volts, I is the abbreviation for amps. It comes from the French, meaning intensité de courant. But often you'll see electricians refer to it as pi, power equals amps times electromotive force. It's the same equation. Pi is the same as watts equals amps times volts, just different preferences. More people are killed each year in the US working on what kind of systems? Well, regular household systems. Probably the reason there, twofold. One is that's the system most people work on. So, you know, there's a greater opportunity to be killed. But I think a lot of electricians, a lot of people become just cavalier about working on those lower voltage systems. When an electrician is working on a very high voltage, you know, dangerous situation, they're typically a little more cautious than when they're just hooking up an electric outlet, you know, in a house or whatever. People get a little bit too familiar and a little bit careless. A kilowatt is just 1,000 watts. So welcome to the metric system, 1,000 watts a kilowatt. And we of course have kiloamps, kilometers, kilometers. A 60 watt hours, 60 watt hours is equal to, well, the best way of figuring watt hours is it's just watts times hours. So 6,000 watts times 10 hours, that would actually be 60,000 watt hours. 240 watts consumed for 15 minutes. So that's 0.25 hours. So 240 times 0.25 is going to be 60. So 60 watt hours. 60 watts consumed for 24 hours, that's going to be, what, 1,200 and something. And 120 for 2 hours, that's 240 watt hours. So really just think of watt hours as watts times hours. It's a measurement of energy as opposed to a measurement of power. When a string of batteries are connected in series, the voltage in the amps remain the same, or voltage increases, but amps remain the same, voltage remains the same, or amps increase, or both voltage and amps increase. Well, when we hook things together in a series, which would be positive to negative, positive to negative, positive to negative, the voltage will increase, but the amps will remain the same. So this is, it's easy to think about this like in the old flashlights, where you had a tube and you dropped 4 D-sized batteries in there, and the positive end was touching the negative end of the next battery, and you had to have 4 of them in there to generate 6 volts, because each battery was 1.5 volts. And so there's no way to remember this except just to remember that series voltage increases, but then if you're hooking up in parallel, then the amps will increase, but the voltage will remain the same. So if you hook 2 positives, 2 negatives together, then you're going to get an increase in amperage, but the voltage will remain the same. So the voltage remain the same, but the amps increase. And the reason you would do that, typically you hook things up in series to get them to the right voltage for whatever your application is. You hook things up in parallel to get enough power to deal with whatever you're using. So for instance, you might need more storage with batteries or more power during the day with a solar array. So you would hook things up in series to get to the proper voltage, and then hook units up in parallel to increase the amount of power or energy that's available. Which of the following is not relevant to DC circuits? Well, if you think about it, a DC circuit is just a flat line. There is no waveform. So resistance comes into play. Ohm's law, which is a factor of resistance, the relationship between volts, amps, and resistance. Voltage drop comes into play. We'll talk about that more. But Hertz is the frequency, the number of cycles per second. And if there are no cycles, as there are none in DC, then that's not relevant. So Hertz would be the issue. And of course, here in the US, we operate at about 60 Hertz, which is 60 cycles per second. Most of the rest of the world, they're going to operate at 50 Hertz. Those are kind of the 2 standards, 50 and 60. When seeking to decrease the effective voltage drop on a circuit, which of the following is not an effective solution? So you can shorten the length of the circuit. That is an effective solution. So, voltage drop is basically the amount of voltage that's lost due to resistance as it travels through the wire. And you can think of that like the friction on the outside of a water pipe. As it moves down the pipe, it's going to lose some of its pressure due to friction. So you can think about that with resistance. As the electrons move down the wire, they're going to lose some of their voltage over distance. Also, the smaller the pipe, smaller the wire, the more the resistance. So in this case, it's saying we could use a smaller wire to decrease voltage drop. Well, that will not be the answer because we need a bigger wire. You can increase the voltage of the system, and that will change the effect of voltage drop. It doesn't change the amount of voltage drop, what happens is, let's say that we're going to be going 1,000 feet over the course of a wire. And we've done the calculations and we find that it will lose about 10 volts as it goes across that 1,000 feet. Well, if you start out at 12 volts, losing 10 volts, you've lost what, 80% or more of the power in the system. That's a very dramatic loss. But if you start out at 1,000 volts and you lose 10 volts, well, it's an insignificant amount. So you increase the voltage, you haven't changed the amount of drop, but you've changed the effect of that drop on the power that's delivered. And this is one of the reasons why we, in the first place, used AC power, is because you could ramp up the voltage. For instance, the very first power station was at Niagara Falls, and they had to send the power from Niagara Falls to Buffalo, New York. So if they tried to send it over DC and it had to be at a fixed rate of like 12 volts, they would have lost pretty much all the power going there. But they could ramp it up using transformers and increase the voltage to many thousands of volts. Then the amount of voltage drop becomes insignificant. So, and then of course, better wire has better conducting properties. So that reduces voltage drop as well. The system designed to eliminate all unwanted current from non-current carrying metal components is referred to as, well, that's the bonding and grounding system. And when we say unwanted current from non-current carrying, well, any metal can carry a current, but only the wire is designed to carry the current. So if you've got conduit and the wire is shorting out to the conduit, then what you want is your system to recognize that and take the transient fault to ground and hopefully notify you that there's a problem. So if there's a short circuit, if there's a ground fault, and the electricity is somehow getting into the grounding system, our systems are designed to recognize that, turn off the array, turn off the system, and give you a warning or a notification that for some reason wire is flowing through the grounding system and it will not work unless you fix that situation. Often with PV, that's going to be a squirrel that's chewed through the wire. And so you'll go out there and you'll find a squirrel hanging by its teeth, you know, on some solar wire, and that's clearly the problem. But this is a safety issue because what you don't want happening is for there to be live electricity on, for instance, the metal frame of the panel. It's just going to sit there until it has a pathway or a load, a pathway to ground or a load to service. So you come out and you touch that panel, you could provide the pathway to ground through your body. So you want to use a bonding and grounding system to give it a better, more efficient pathway to ground, to deflect that from the human body. So that's the whole purpose of a grounding and bonding system. It is there as a life safety issue. Bare wire or green insulation will always indicate that the wire is part of the bonding and grounding system. So I always used to wonder why bare copper wire was, I mean, I thought, wouldn't people get shocked? You know, there's no insulation on it. Well, it's not supposed to carry electricity unless there's a problem. So it really shouldn't be an issue. If it is an issue, somebody's going to get shocked regardless if they touch any metal part. All right, the loss of an electrical signal over distance as it travels along a conductor due to resistance is referred to as, and this is the voltage drop. So as we lose signal over distance, and one thing to consider is, like the first law of thermodynamics says, energy is never created or destroyed, it simply changes form. So if we're losing power over distance, that power loss is converted into heat. So the inefficiency of resistance will result in heat building up within the conduit and within the system. So we have to have a way of dissipating that heat as well. All right, the document that details industry best practices from a safety perspective in the US is the National Electrical Code. And as we talked about last time, that's also referred to as NFPA document 70. But the NEC is a safety document. It does not really care if your system works or not. It's there to provide safety. It also doesn't care how much it costs. So, you know, they'll put recommendations in there that will add a lot of expense to your system. They don't care. It's not their concern. It's all about health and safety. The 8-foot long metal rod, commonly called a ground rod, is more accurately referred to as the grounding electrode. And we do in residential systems use grounding electrodes for the most part. But in some commercial systems, you'll find, for instance, like an UFR ground system, which is the grounding systems built into the rebar that makes the foundation of the building. So you don't necessarily have a ground rod, but in residential systems you would. When referencing the resistance characteristics of the various conductors or wires, the NEC measures in ohms per 1,000 feet. So when we talk about the Ohm's law, which is another one, I'll go ahead and screen share here on the whiteboard, but we will often refer to this Ohm's law. I like to say V volts equals amps times resistance. And all this is a relationship between volts, amps, and resistance. This is one of the equations you'll need to know for the exam. The power equation is watts equals amps times volts. So these are not very difficult equations. But the third equation that we're going to need to know is voltage drop. And voltage drop equals volts. Voltage drops equals amps. And what amps are we talking about? Well, normally we're talking about the amp rating at the maximum power point, which is the rating on the panel when it's operating at its under standard test conditions, times resistance, times twice the distance over 1,000 feet. So this is the voltage drop equation. Well, if you look at it, it's Ohm's law adjusted for distance. That's all it is. And why did we have to adjust it for distance? It's because the resistance characteristics that were given is in ohms per 1,000 feet. So for instance, if you're looking up in the NEC and you're using, say, number 10 gauge wire, and you're going to find it has 1.24 ohms per 1,000 feet. So that's going to be the resistance you're going to plug into this equation if you're using number 10 wire. So we're going to use our amps, which we would get off our solar panels. So let's say we've got a string of solar panels and the IMP, or the amps at the maximum power point, is 8.6 amps at that panel. Well, regardless of how many we've hooked up in string, remember, when we hook up in a string, the voltage increases, but the amps remain the same. So for each string, it's going to be the amps for one panel, because the amps don't change when you hook it up as a string. So in this case, I might put 8.6 amps. I got that off the panel. I'm using 10 gauge wire, so I'm going to use 1.24 ohms. 1.24 ohms here. But that's per 1,000 feet. So now I need to know how many feet my run is. Well, let's say that the run is 250 feet. I use twice the distance. Well, why do I use twice the distance? It's because it's a circuit. So the wire goes there and the wire comes back. So the electricity is going twice the distance. So in this case, if the distance were 250 feet, I would put 500 feet divided by 1,000 feet, because this ohms is per 1,000 feet, or I could get rid of that and say times 0.5. And now to figure out my voltage drop, I just take 8.6 times 1.24 times 0.5. And I don't have my calculator here, but I'll just say that's going to be about 10 times 0.5, or about 5 volts, more or less, somewhere in there. So right around 5 volts, more or less. You guys could figure it out. So basically, over the course of that run, from beginning to end, I'm going to lose 5 volts. Well, is that acceptable? It depends. It depends on what the voltage of your system is. If my system is 12 volts, well, I've just lost about half of my power. Clearly, that's not going to be acceptable. But if my system is 600 volts, which is standard for a residential PV system, well, now I'm losing less than 1% of my power. And what we're trying to do is get our voltage drop in our system, ideally to be less than 2%. That's kind of where we're going to go for. We want overall to be less than 2%. So, so this would be acceptable if I'm losing 5 volts out of 600 volts. I could reduce that by going with bigger wire, and that way I would have a lower resistance, the bigger the wire, or I could shorten the distance. But you should shorten the distance anyway, just to make your system as efficient as possible. So this is the whole concept of voltage drop. It's just Ohm's law adjusted for distance. And we reduce our voltage drop by going with bigger wire, shortening the distance, or increasing the voltage of our system. Those are pretty much the options we have available to us. So did anybody have any questions on that? I see a chat thing there, Don, Greg. 5.38. Okay, so I was right. Lost about 5 volts, more or less, 5.38 volts, to be exact. All right. So that was a long explanation about voltage drop. But that's probably in this chapter the one concept that's the most difficult for people to grasp. When a circuit is closed, what are we talking about with a closed circuit? It allows energy to flow through it. So a light switch that's turned on is a closed circuit. A light switch that's turned off is an open circuit. So by closing the circuit, the electrons can flow through it. You can think about it like a gate in a fence line. If you open it, you've broken the continuity of that circuit. 6 panels are connected in series. Each panel has a VMP rating of 18 volts, IMP rating of 8.33. The output current of this string will be, well, the current is 8.33 amps. 6 panels connected in series, doesn't matter how many in series. It could be 100 panels. It's amps don't increase. So the answer is going to be 8.33 when you hook things up in series. Another hint is it's the only current reading here. All the rest are in volts. So if you understand the difference between amps, volts, you're not going to miss that one. 6 solar panels are connected in series. Each panel has 18 volts DC, amp rating of 8.33. What's the output voltage? Well, volts increase, so we would take 6 times 18. That ends up being 108. But it's DC current because these are solar panels. So it's 108 volts DC. Most people are used to just dealing with volts. They assume it's AC. But we're now in the world of AC and DC. So we should designate whether it's AC or DC. So it's a volts DC, direct current, as opposed to alternating current. Ohm's law is expressed as, well, that's a verb, right? Volts equals amps times resistance, or volts equals current times resistance. Okay, so far I'm getting them all right. That's good. When measuring the terminals of a blown fuse with a multimeter set to perform a continuity test, the resistance, well, if the fuse is, if it's an open circuit, which is what a blown fuse does, resistance is infinite, right? No electricity is flowing through it, so you have resistance of 1 or infinite. And that's basically what you would call a continuity test. You're just seeing if there's infinite resistance, there's no circuit. What is the voltage drop of a 400-foot cable run using number 10 stranded copper wire on a circuit designed to carry 8.3 amps and 48 volts of electricity? All right, so we know our distance, 400 feet. We know the size of the wire, and we know it's carrying 8.3 amps. So we use our voltage drop equation, which is voltage drops equals amps times resistance times twice the distance divided by 1,000. Well, what's the resistance? That's why we gave you the resistance table. For stranded copper, it's 1.24 ohms per 1,000 feet. So our equation would end up being 8.3 times 1.24 times 2 times 400, which would be 800 divided by 1,000, or 0.8. So we have 8.3 times 1.24 times 0.8, and we end up with, starts out at 8.3 times a little more than 1 times a little less than 1, or 8.23. And I've got it worked out here. So here's our voltage drop equation, amps times resistance times twice the distance. So we have 8.3 amps times 1.24 ohms times 800 feet. It's just easier to divide the 800 feet by 1,000 feet. So we get 0.8, and it's now 8.23 volts. So voltage drop equation, pretty simple once you have that equation memorized. And the best way, if you're familiar with Ohm's law, is just say it's Ohm's law adjusted for distance. That's all it is. All right, as I move into the next one, does anybody have any specific questions at this point? Because I'll just keep rocking forward here. What percentage of power loss due to voltage drop? Well, we know that we lost 8.23 volts. It's a 48-volt system. So we divide 8.23 by 48. We find out that we've lost 17%. Well, is that acceptable? Well, we've said no. You know, we want to keep everything below about 2%. So we've lost this. So our alternatives are use a bigger wire, shorten the distance, or increase the voltage of our system. The most dramatic effect is going to be if we can increase that 48 volts to 600 volts. You know, that will be the most dramatic impact. Cycles per second are referred to as hertz, right? Most of these names like hertz, ohms, joules, these are all named after dead white scientists, you know. Back in the 1970s, they changed the names of a lot of these. Before it was called hertz, it was referred to as cycles per second. But they were used now, standard international units are now referred to as hertzes, ohms, joules, newtons, watts. All of these are like old dead white scientists. Which of the following is not measured, is not considered a major component of the grid? Well, generation is a major component. Transmission takes it from the generating facility to the local distribution system. And then, of course, the distribution system. So harmonization out of those is the odd one out. So you have generation, transmission, and distribution. So that's taken us through the basic electricity. Just to reiterate, you need to understand, or you need to memorize basically the three equations. Watts equals amps times volts. Volts equals amps times resistance, or VER, that's Ohm's law. And those are just telling you relationships. You have to know two of the variables. If you know two of them, you can figure out the third. And then you need to know voltage drop, which is a variation, is basically Ohm's law adjusted for distance. So those three are the big deals. Hopefully this is review for most of you. For some people, it may all be brand new. So before we call it a day, does anybody have any specific questions here? Anything? I can see Chad, but I can't see the others. Nope. All right, I'm not seeing anything pop up in the chat. So at this point, we'll get together at 1 o'clock on Friday, and we'll do chapter 5. Okay, chapter 5, now we're starting to get into the meat and potatoes of the system. You know, this has all been review up to here. All right, so talk to you later. Bye-bye.